So the packet from China has arrived, and let's pick one of the PCBs out and see what it looks like. Well, this looks pretty neat and tidy to me. This is the front side and the back side. Well, I can't see any visual problems with it, or see any problems with visual inspections at least. So let's just take a quick check of seeing how big this is and compare that to what I specified. I specified that this should be 85.34 millimeters. Oh, the battery in my caliper is running out. So this seems to be 85.44 approximately, or 85.38. Oh, which is very nice. It's just 3 or 4 1/100ths of a millimeter wrong in that direction. And in this direction we have 99.82, which is pretty close to what I specified. Alright, so far no problems whatsoever. Let's just make a quick check that the sockets are properly sized. This is the EEPROM socket and should go right over here. Just as I thought. And then we have another 20-pin socket that typically goes into here. Works just nicely. So now I should just mount all the components and be back shortly. So let's verify the reset vector board. This is the reset vector board with the logic and the EEPROM. These are the dip switches for setting the reset vector, and these are the connectors which I attach it to the rest of the system, the bush I call it. We have the address bus, the lower and upper 8 bits. We have the data bus, 8 bits. We have the read and write signal, and this is just connecting the card address to 0, which places the reset vector board at control space address FF80. It should really be FF00, but there is a problem in my design, which I didn't review properly, which enables bit R7 over here, which means that it's pushed up to FF80 instead of FF0. We can do the verification anyway, but it should be fixed by a patch later on. Another error that I discovered was that according to the specification in the control space, the data space active bit should be on bit 0 on byte 1, but apparently I did the design too quickly, so I placed it on bit 1 on byte 1. So that means that we have to manipulate bit 1 instead of bit 0. So let's proceed with the actual verification. So first we power it on, and then we verify that according to specification the bit DS active should be 0 to make sure that the card is by default activated. And I happen to know that is on pin 5 on U9, and it should be 0. Yeah, it's 0.26 volts. So logically that counts as a 0. Good. So now let's try to read the reset vector's upper address, and then we put this to F, all ones, and then F, and then 2 zeros at the end, so this is actually C. And I push this switch to get a read. and we get 100000111, which happens to be exact the setting of this dip switch. 100001111. Perfect. If I now move to the D address and read, I get 101000011, which is exactly what it says here. 101000011. So the address overloading works just perfectly. But let's write 1 into the control register's bit 1 so that we deactivate the address overloading on the CPU memory space, and see if we after that read the reset vectors and we get an undefined result on the bus or not. So let's write all zeros except bit 1, and then we put in the control register 1 address, which should be FF01, but because of the bug I mentioned, it should be this one should be set to 1. Then I flip this switch to write it, and we set bit number 1. And then we should verify the DS flag bit 5 to be 1. Yes, 4.4 volts. It's counting as 1. And then we can read the reset vector address again, FFC, and then we do the read. We see that they are undefined values. They are floating, and the CMOS transistors are giving any value given the current charge state they are in. We also have to verify that the CDD signal is actually not activated, and I happen to know that this is an active high signal on this pin and it is low here, so it's inactivated. We can also check FFFD and do a read. See, that's the same thing. It's undefined bus and the CDD signal is low. Works just like a charm. So let's turn this signal low again and write that into the control register 1, like this. So now it's all zeros, which means that bit 5 should be 0 again. 0.25 millivolts. And that means that the address overload is in place again. So if we read the reset vector once again, FFFZ, and read, we get back our nice preset vector, and also D, we get that same reset vector verified again. So the address overloading is just working fine from a purely logical standpoint. Then we might have to make sure that the timing and the response times are working well as well, but that is a later problem. I have experimented a little bit more with this reset vector board, and I have discovered another bug, and that is that when I perform a read from control register 1 when the bus is driven from elsewhere, that actually acts as a write. For instance, if I start out with writing E8 to control register 1 like this, I see that it turns out correct as E8. But then if I read from somewhere else and make the board drive the bus, and read from FFFC, which is part of the reset vector, I get A3, which is perfectly okay, which is what I've been expecting it to be. But then if I go back and read from control register 1, I would expect it to be E8 again. But when I do that, I see that now there is actually A3 stored in there. And this means that there is a transient on the clock pulse into the clock input on U9. That is a 74LS273. And that is most probably due to that I have different signal delays in the address decode logic over here. Some signals are going past these circuits, like the address parts of the address bus and the read-write signal. But some other parts are going through this one to generate the MSB's FF signal and LSB's in control space signal, which means that during this time delay period these outputs may flicker up and down. And what happens is that when this read path comes, it actually briefly generates a low signal on control register write enable that goes down here and clocks in whatever is read that is driven on this bus. And that is of course not good, so I've devised a solution where I put in a capacitor on this line to make sure that it actually stays high for these 20 nanoseconds. And that capacitor is attached on the EEPROM output here between control register output and the ground signal. And experimentally I have verified that to be the acceptable values are between 1 picofarad and 300 picofarad. But I'm not satisfied with just an experimental value that seems to work. I want a theoretical justification as well, which we can see here. The delay going through this 74 LS688 is roughly 20 nanoseconds. It can be less and it can be more, but the typical value is 20 nanoseconds. And by looking up the data sheet of the buffer, we can see that it draws 0.4 milliamps when the signal is low, which means that the total charge that it consumes during this period is 0.4 milliamps times 20 nanoseconds, which amounts to 8 picocoulombs. And we don't want the voltage to drop more than about 1 volt, which means that I need to use a capacitor of 8 picofarads, or a nice and round value of 10 picofarads, which lies exactly in the range of the experimentally verified value. So I will put in a 10 picofarad capacitor on this signal to prevent this from happening again. So this is the patch board, and on the back side you can see the fix for the 2 bugs that I've discovered. These 2 are the bit that went on the wrong position, bit number 0 instead of bit number 1, and this is the capacitor for the clocking. I actually went with a slightly larger capacitor value for this, and I'm not 100% satisfied with the explanation I did last time, and I think this might come back and haunt me in the future. It works, this patch, but I don't think I have justified it as good as I can. So now let's do a last test on this reset vector board. It should fit into the casing, and the height should be 100 millimeters, the width should be 1.2 millimeters. It slides in pretty nicely. It is a little bit short. The full length is 160 millimeters, but it was too cheap to actually manufacture it to the full length. It would be a little bit more expensive, and this means that it will be hard if I have many boards to actually access it in here. But I think I can deal with that problem later on. This is the power supply connector, and on the back panel over here, the corresponding one, there should be a connector for attaching the external power supply. Also, the thickness of this board and the PCB guides isn't perfect. You can see that it's jiggling a little bit. The other PCB that I tested in the previous episode, which was an experimental Euroboard, didn't have this wiggle thing, so I probably need to adjust the width of these for future expansion ports.
That's all for this episode. Next time we'll take a look at the construction of the main board and the backplane board, do some simulated mechanical integration testing between paper printed PCBs and 3D printed items before sending them off to production. See you next time!